So Namaskar, good afternoon. I am Satyaji, pursuing MTech Defense Technology, second semester in UIT Kurukshetra University, Kurukshetra. So today I am going to present my second semester seminar as I lost my connection during the presentation. So sorry for the inconvenience and let me give a second chance to present my seminar. So I'll start with my presentation. So the topic is advanced weapon system. So first we'll start with what is weapon system, type of weapons and their working process, and in the end we'll talk about missile, how to improve its efficiency, stability, firepower, survivability, and the uh, overall efficiency, and what the factor you have to modify to create a weapon system, advanced weapon system from a weapon system. So weapon is a tool used in combat. Weapon is an instrument used for the purpose of defeating, killing, or injuring the enemy. So enemies are of like the weapons are of different kinds. That can be a mace, sword, and like which we can use in hand, or it can be a small ammunitions like bullets, then pellets, and it can be a big projectile like heat, gas, and rockets, motors, and it can be a missile. So in this topic we will more focus about the weapons that will be the backbone of the defense force of a country in upcoming few years. So in the image we are seeing the Cat Warrior series, the prototype, the showpiece displayed by the HL. So HL Cat Warriors are a group of uh, advanced weapon systems which are under development. So the down one is a UAV, and the attached weapons in the pod of the Tejas are the advanced weapon systems. So before going to weapon system, we'll talk about survivability onion. Survivability onion tells us how to avoid detection by your enemy, or how to prevent acquire by your enemy, how to prevent heat, how to prevent penetrate, and how to prevent kill. So basically this is a topic which tells about how to improve your survivability percentage. At the same time we have to consider more to improve our firepower, weapon effectiveness index, and the killing capacity, improving destructiveness. So these are the few weapons which are now are in service in defense forces of India. So the left side one we have explained about it shows the range and the new uh, modern weapons or modern weapon systems. So basically there are some missiles like Prahar, BrahMos, which are for short range, and the Prithvi is also in short range. But starting from Agni, so Agni 1, 2, 3 are medium range missiles, and Agni 4 and 5 are intercontinental ballistic missiles. So in between the Nirvai comes where the terms come ballistic and cruise. The Nirvai is a long range cruise missile. However, most of the other including Agni series are the ballistic missiles. So whether it's a ballistic missile or a bullet, first we have to focus about their safes. So it depends upon the range, the nose cone or the worded shapes are different. Each it amplifies their range. At the same time, it reduces the drag and increase the stability and performance. So similarly for bullets, the projectile is also having some shape, depends upon their range, their stability, and the penetration capabilities. So I will start with a simple example of a rocket. So whenever we come across like some country launch a rocket for other for its enemy, so we are feeling doubt with we are using the rockets for satellite or for space exploration. At the same time, how we can use it for a war. So basically, the rocket are and the missiles are just differ by their the payloads, but almost all same for a like the configuration are same. So basically, a rocket have a payload, a propulsion system which may be a solid or liquid. So the igniter and the nozzle which generate the thrust by burning the propellant. So then we come to a missile. So missile is a guided airborne range weapons capable of self-propelled figure usually by a jet engine or a rocket motor. So rocket are almost similar to a missile except their payload capabilities. So this is the left side is showing the first glide bomb which is made by Germany, the V1, the flying bomb, and the second one is a proper explanation of a missile which is V2 or it made by the same nation Germany during the First World War. So coming to the weapon system components. So the missile consists a warhead, a guidance and control system, a fuel tank or propulsive systems, in the rocket nozzles, motors or a turbine, gas turbine engine or like some engines which will generate some thrust producing device, and the control fins or like the control like aerodynamic controllers. So basically we divide them into targeting system, guidance system, then flight system, engine and warhead. Talking about the guidance system, a guidance system may use the radio wave, microwave, lasers and other things which will give some input to the guidance to input for uh, guidance of the system. The and target system acquire the data from the guidance system and by finding its position by either using inertial navigation system or telecom, it will try to head toward the enemy and it will generate some response and or some outputs. The output will go to the flight control systems. So for flight control system, they are having some movable or deflecting aerodynamic control surfaces, which will tense the system to aim toward the enemy or the target. So it can be happen by two ways, either by vectoring the thrust, which will lead the system to direct toward the target, or by deflecting the control surface. So that are basically wings, fins, canards, those things. So the most important system which contribute the most for the range of a missile is the engine system. So engine systems are like the propulsive systems of a missile are just to use the to uh, just provide the thrust, or it it leads the system to move. So rocket are generally the solid propellant types for case of maintenance and fast deployment. Although some larger ballistic missiles use rocket propellant. So there we come about the stages. So most of the rockets or the missiles for ICBM purpose, they use the solid propellant booster phase followed by the liquid stages, which gives some extra velocity to get the top position in the ballistic curve, and at the same time it will increase the terminal velocity. At the same time, for a short range and lightweight, we have to depend upon the air breathing systems, which include the ramjet, scramjet, turbofan engines. So it can be a centrifugal propulsive system, axial, or can be mixed mode. So warhead are nothing but the primary destructive component or primary firepower component, or also it provides the destructive firepower to the missile. Missiles generally have one or more warheads. So compare like in future, the Agni 6, the Agni series, the next one is Agni 6, which is going to be a MIRV. So the missile which have more than one warhead will call it MIRV, multiple independent re-entry vehicles. So we'll talk about the merits and demerits of a MIRV and how to improve its efficiency in some time. So missiles are generally categorized by their launch platforms, intent targets in broadest term. The launch and target are either surface or air, uh, or in sea or inside sometime a sea. The missiles can be subcategorized by uh, the target type. There are maybe like anti-tank which are on the surface, anti-sea, also it can be anti-submarine missile. So first we'll talk about ballistic and cruise missiles. So ballistic missiles are having a long range with a very high terminal velocity. At the same time, the cruise missile are operate within a very less altitude, below 100 or 200. So they will breathe air, and it will use the air breathing propulsion system to cruise or to propel the system. So it can be a hypersonic glide vehicle. The first phase of the any hypersonic or supersonic glide vehicle will be a booster, which will provide some initial velocity. So after the first phase, the booster will be separated from the missile, and the gliding system will glide. At the same time, the hypersonic cruise missile will be flying at very less altitude than that of the glide vehicle. A ballistic missile is a type of missile that uses the projectile motion to deliver the warhead on a given target. So these weapons are only during the relative brief periods. Most of the flights is up power. Then after At a short range, the ballistic missiles stay within the Earth's atmosphere, while interconnectional when intercontinental ballistic missiles are launched on a suborbital flights. So basically, the given figure shows MIRB. So first I'll come to a ballistic missile. So ballistic missile we have single warhead, and for first few stages like the booster stage, solid liquid propellant stage, it will take the warhead to a peak position outside the atmosphere, and then it will lead to a free fall. During free fall, the terminal velocity will reach something Mach 15 to 20. So at the same time, you can use more than one warhead for the ICBM, which we will call MIRB, multiple independent re-entry vehicle. So for that, it will have more than warhead, and at the peak point, it will separate, or it can separate followed by one followed by another. It will drop uh, more than one target. It can destroy more than one target as it have more than one warhead. But at the same time, it will reduce the accuracy and instability. We'll find the solution for the instability and accuracy improvement. So after the ballistic missile, we'll come to a cruise missile, which is a guided missile used against terrestrial or naval targets. Basically, for a for a denser region, if you want to destroy a particular target without harming the other um, other uh, geo like other houses, other buildings, um, other systems. So generally, it improves the accuracy, and it destroys the particular target, which is a good point. So cruise missiles are designed to deliver a large warhead over long distance with high precision. So modern cruise missiles are capable to travel at high subsonic, supersonic, or hypersonic speed. So coming to a subsonic cruise missile. So basically, the cruise missile travel less than Mach 1. It used either axial, centrifugal, or mixed turbojet. So the missile range can vary from 500 to 1000 kilometers. So the River, which is India's own developed and designed by DRDO cruise missile, which is propelled by turbofan engine. So we call that engine as a at the same time we also talk about the supersonic cruise missiles. So whenever the term supersonic cruise missile come to mind, our mind goes to BrahMos. India's and Russia's jointly developed missile, which have a capability of Mach 3.2 at high precision. Supersonic cruise missiles are traveling faster than the air, below Mach 5, and it can range from 100 to 500 general. So hypersonic cruise missiles are the missiles which travel at Mach 5. So India developed the hypersonic test demonstrator vehicle, which will be the delivery system for next generation hypersonic cruise missiles. So hypersonic systems are having the intake, combustor, and nozzle. During the intake, the shock waves will compress the flow, and in the combustor, the fuel will be injected to the high pressurized or the more energetic matter energetic fluid which is compressed from atomic pressure to more than 5 times or 6 times, which will the, when the fuel inject, it will burn, it will create the thrust by moving through a diversion nozzle or conversion diversion nozzle. So basically we talked about three things. One is firepower, mobility and survivability. When we talk about firepower, it's all goes to the primary destructive firepower of any system, which can be provided by its warhead or a projectile for a bullet. So our first topic is how to optimize the efficiency, how to improve the efficiency by optimizing the instability and drag due to the conventional way of grouping the errors in a MIR. So second topic will come to a mobility, which refers the propulsive efficiency, how to improve the propulsive efficiency, which can be achieved by either compressor, combustor, turbine for a gas turbine in air breathing engine, or by improving the nozzle characteristics of a non-air breathing engine. For air breathing engine, I'll be more focused about the compressor designs and then optimization. So we'll go for centrifugal compressor design, and also that can be done for the axial, which I'll be doing later. And regarding the nozzle optimization, I'll talk about the aerospike nozzle, which is the upcoming futuristic nozzle for the weapon systems. It can be also used in the hypersonic missiles. So survivability, as you know, first in the second slide I told, in the survivability only, the first thing to improve the survivability is avoid detectability, to avoid detection. So to not get detected by the enemy radar, most of the missiles are required to fly at low level. So at low altitude, the radar will be less effective to detect the missile system. Also, at hypersonic at low altitude, it will be almost negligible to get detected by enemy. So for that, we need a hypersonic propulsion system with an improvised intake. So the first topic is the grouping of warhead. So as I shown, if the missile is for a missile or weapon system, the firepower is nothing but the effectiveness of the warhead, its range, stability and accuracy. In 2013, DRDO Chief B.K. Saraswat said that India is already in a way to improve the Agni 6 indirectly. So it's a public domain data. So India has already started its mission to Agni 6. So Agni 6 will be a MIR. What is MIRB? MIRB is a multiple independently targetable re-entry vehicle. So multiple independently targetable re-entry vehicle, or generalized term is multiple independent re-entry vehicle. So they are having multiple warheads which are independently can target more than one targets. So the left side picture shows how the multiple entry vehicles are entering into atmosphere. So they can fall at a distance 800, like you can take any less distance, but it can go up to 800,000 kilometers apart from each other. It can fall. So at one missile, by using one missile, you can destroy multiple targets of the enemy. So before going to multiple word grouping, we have to check the efficiency you have to check about the efficiency of each kind of warhead. So these are the some basics type of warhead. Starting with left, it's a spherical, then elliptical, then ogive, then different kind of ogive. Then right side top, it's a cone, then spherical headed cone, blunted conic, then blunted ogive, then bicone. Like that, there are so many more warheads types which I have designed myself by taking the coordinates, which I designed the coordinate calculator where you can enter your radius and some features of the warhead set, and you can easily get the coordinate system. You can easily get the coordinates which you can import in any design software, and you can make the warhead type for your test. So now I am introducing the VSCC, so that is of the VSSC type of warhead. So in the right side we have shown the conventional way of grouping of MIRV bus. So the first one is 10 warhead bus, then the 5 warhead bus, then whether the people like it is a grouping, and in the down it is 3 warhead bus. So I have taken the 3 warhead bus and I have designed myself. So the left side is showing the CAD model, the CAD model of the MIRV bus, which is having 3 wards. So after separating each of warhead, they are creating some more wetted area, which will create more drag. At the same time, it will make the bus instable. It will instabilize the bus. So to optimize the instability and the drag and to improve the efficiency, I have suggested the variable swept spike code VSSC grouping method. So here I have used a spike in the tilted warhead in the given shape where you can optimize the drag and the instability. At the same time, you can improve its range and efficiency. The main difficulties for a blunt body problem is the mathematical modeling of Reynolds average Navier 20% or any kind of mathematical modeling. As there are two regions, one is sonic and one is subsonic region. So like subsonic and supersonic or hypersonic region. So the mathematical model will behave as a optical equation inside the subsonic. After the sonic line, it will behave as a hyperbolic region. So that is a main problem to do the analysis. But as we know, the strong curved bores have sit in front of the blunt nose detached from the nose by distance delta, called shock detachment distance. The main difficulty in the presence of subsonic and supersonic regions. Therefore, the flow is inviscid, hence the governing equations are Euler equations which can be exhibit the mathematical behavior of ellipse and hyperbolics, steady subsonic and steady supersonic relation. So the second part, as I told, the propulsive system is to be efficient to improve the range of the missile or the system. So first I'll talk about the nozzle, the aerospike nozzle, which can be a solution for the overexpand and underexpand situation for a bell contour nozzle. So the aerospace nozzle can improve that. So second part is the air breathing engine, where I'll discuss about the centrifugal compressor. I will uh, I will take you to the Excel where I have generated the calculator where you can generate your impeller characteristics, like your thickness at the exit like the exit like what do you call it, like diffuser throat thickness. At the same time, we'll talk about how to improve the efficiencies of a compressor. So as the pressure ratio play a major role in the efficiency, so the best way to improve the efficiency is by increasing the pressure ratio by optimizing the compressor. So here I have shown the centrifugal one. We can do it for the axial one also. So this is the calculator where you can get your pressure ratio, then the air inlet angles at hub and at shroud. So also you can get the depth at outlet, the axial depth at outlet. So last but not the least, as I told, for survivability we have to uh, increase the velocity of the system at low altitude. So for that there is only the most efficient way to do that is by using a hypersonic or a supersonic system. So for that we have to improve its intake, which will reduce the distortion created by which will reduce the distortion and improve the efficiency of intake, which further can be improved by using a good ramjet scramjet engine, or it can use the gas turbine engine, which will result into the advanced performance of the system. At the end, we will be able to create a new advanced weapon system. So before going to conclusion, first I'll take you to the research fields. So to avoid the error, first I will go for the warhead grouping. So before that, first I took a single part, like single warhead, a conic one with a blunt body. So I did the analysis. So to represent that, I'll show you the screen recorded video that I am finding more convenient this one. So first I import the model which I have generated by using the coordinate calculator prepared by me. So for that, so these are the different kind of single warheads. So for any one, like second anything, you can go inside, click, and it will take to a coordinate calculator where you can enter the parameters like R, L, and the angle and the R12 ratio. It will give you the coordinates by using which you can generate your own like overhead shapes for for a given diameter or R like L to R ratio. So these are the files, the CAD files which I prepared by using Alex. So after that, I imported it in ANSYS Workbench. Then I have created the separate surface which will help me to mesh easily. Then I have created the domain. Then I have treated it as I found it is symmetric, so it will be helpful for to reduce the computational time. Then I have gone for surface split. Then I did the meshing, which is a first it gave me a coarse mesh. Then afterward I have improved it for a finer mesh by doing edge sizing. Then in the end I have ended up with a fine mesh. After that I took it for that CFX, and I did the CFD analysis by following the conventional methods. Then at the solution it get converged after 100 runs. So after that I have gone to post, and I generate and I recover the symmetricity. And then by various post parameters I found the pressure distribution, mark distribution, and I found the pressure distribution in the x direction, from which we can find the forces like x forces and y forces, z forces, and then we can calculate the drag. So this is the streamline. The pressure variation, pressure control we can show, and the heating effect toward the nozzle, toward the nose cone, you can also see. Like that I have to do for all. So similarly, the second thing is by using the vistas CCD, how I created the centrifugal compressor, which I'll be going for the axial one in the upcoming days. So first I generated the centrifugal blade by taking the data from the calculator. So let me take the calculator. So by using the design calculator for the centrifugal compressor, you can enter the data, uh, the parameters for your desired centrifugal single side centrifugal compressor. You can enter your data and the air constants like CP and other things. It will give you the pressure ratio, the depth, and the air inlet angles. By using this data, also you can change it and you can get your desired data. Let me change the RPM to 500. It will give you the corresponding value. Let it be. So we are getting pressure ratio at 4, or somewhat 4. So you can change the air inlet angles, the diameters, the intake area and everything. So after that I did the turbo grid meshing. Then I took it for CFX for analysis. Then after the CFX, I also set a parameter of back pressure. So I can change the back pressure and I can get it back for. So this is the pressure distribution, and also we'll check the flow and where it is getting separated. So why I need the splitter blades, then like how many splitter blades you need, and other like parameters as surge margin, stall margin, you can calculate. So similarly, you can go for a hypersonic intake, which I am in the design phase of its intake. So here basically I am going to design the intake by using the coordinate systems, and in the upcoming days I'll explain the uh, topic how to optimize the intake characteristics. So in the conclusion I would like to say, so first we will create the CAD parts of everything, each component of the missile, where we have to optimize for a uh, improvised to, to improvise its characteristics. So first we'll make the CAD designs by doing the literature studies. Then we'll go for the analysis, either it may be a CFD or structural analysis, and then we'll optimize the geometry, and in the end we'll create a CAD model of the advanced weapon system, which we can compare with the baseline model, and we can evaluate the weapon effectiveness index, how much it is improved by using the weapon effectiveness index calculation steps. So thank you. Jai Hind. If you have any doubt, you can mail me or you can drop me in the comments. Thank you.